Hello, maths people. Welcome to Maths with EJD. In the last video, I began to talk about the Cayley-Hamilton theorem. So in this video, I want us to look at at matrix inversion by Cayley-Hamilton theorem. Before now, we've seen matrix inversion by different methods like the minors and cofactors method. We've also considered we've considered the Gauss-Jordan method, the Gauss-Jordan method. We've also considered the matrix inversion by solving systems of linear equations. And then now we are talking about about matrix inversion by Cayley-Hamilton theorem. So I mean, you have all these different methods. So you may, by having gone through all of them, you can now choose one that you really like to stick with. So far, I would think that the Gauss-Jordan is still like uh the best, especially if you are dealing with large matrices. So it all depends on what you want. Okay, so matrix inversion by Cayley-Hamilton theorem. Given a matrix A, right, well, be it 2 by, of course, it has to be a square matrix, as you already know. It has to be a square matrix. So given a matrix A, the first thing you want to do, just like we did previously, is to obtain the characteristic polynomial, which is rho of lambda. And the definition is this: rho of lambda is equal to the determinant of your matrix A minus lambda I. Lambda is a scalar. Lambda actually has a special name, which you are going to find out probably after this video. I'll be talking about eigenvalues and eigenvectors, so you get to see all of that. Okay, so given a matrix A, you obtain the characteristic polynomial rho I, which is defined this way. And then having obtained the characteristic polynomial, you have to substitute A for lambda, just like we saw in the previous video. And in that case, you get rho of A, which is 0, because Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic polynomial. That means that when you substitute A for lambda in the characteristic polynomial of a particular matrix, you get 0. Okay, so and once that is done, just the way you got higher powers of your matrix before, you can also multiply through by A inverse, and then by having multiplied through by A inverse, you can make A inverse the subject of formula, and then you evaluate the ensuing expression for A inverse, just the way we did for things like matrix raised to power 3, 4, and things like that. Okay, so let's dive into it. Let's see a 2 by 2 matrix as our practice is. So here you have to find the inverse of 3, 1, 2 minus 1 using the Cayley-Hamilton theorem, CHT. Okay. So of course the first thing is to find the characteristic polynomial, which is defined as q minus lambda I. Our matrix now is q. So you have q minus lambda I. And of course, that is going to be 3, 1, 2 minus 1 in minus lambda 0, 0 lambda. So at the end of the day, the lambdas are going to get attached to the elements on the principal diagonal. So you have 3 minus lambda 1, 2 minus 1 minus lambda. And then you go ahead to find the determinant as we've always done. So that means this multiplied by this, that's what you have here, minus 2 times 1, that is this. And then you can expand as 3 times minus 1, that's minus 3, 3 times minus lambda, minus 3 lambda, minus lambda times minus 1, that's plus lambda, minus lambda times minus lambda, that's plus lambda squared. 2 times 1 is 2. So what we have to do next is to tidy things up. You have lambda squared, that's this. Then minus 3 lambda plus lambda, that's minus 2 lambda. Then minus 3 minus 2, that's minus 5. So that we've collected all the like terms, So basically, this is the characteristic polynomial for this matrix you have up there. This is the characteristic polynomial. So, but then we are looking for the inverse, right? You already know whether we prove it or not. We already know that when you put the matrix A into this characteristic polynomial, it is going to give you 0 because it's a law. So what we did in the previous video was to prove it. So to prove it, you put the matrix, you square the matrix, you multiply it by 2, then you multiply the unit matrix by 5 and evaluate, you're going to get 0. I mean, it's sure. It's not like sometimes you get it, sometimes you don't get it. As far as it is a square matrix, it will always be true. So that's why I'm not bothering to prove anything here, because our focus here is to find the inverse. You already know the law always holds. So since we know that row A is always 0, and of course, and our row A in this case would be anywhere you have lambda, put A. So you have lambda squared now becomes A squared, minus 2 lambda becomes minus 2A, then minus 5 becomes minus 5I. Of course, I've told you, since you are dealing with matrices now, it will not be proper to just put 5. So you have to multiply 5 by what is the equivalence of 1 in matrix form. Especially here, we have 2 by 2. So you have row A equals A squared minus 2A minus 5A. According to Cayley-Hamilton, like I said, row A is always 0. As far as A is a unit, is a 2 by 2 matrix. Like that, row A is always 0. So that's why row A is 0 here. And that's equal to A squared minus 2A minus 5I. And our focus is to find A inverse, the inverse of A. So what we can do is to multiply each term by A inverse. If you multiply 0 by A inverse, that's 0. Multiply A squared, A squared multiplied by A inverse. That's like, you can even do it like, what is indices, right? 2 minus 1, 1. So that ends up being A. Then you have 2A times A. So 2A times A inverse. That means this is raised power 1, right? So that's 2A raised power 0. And A raised power 0 is 1. So that's just 2. But instead of just writing 2, you have to make it 2I because you're dealing with matrices. And then you have 5I multiplied by A inverse. Of course, A inverse, I multiplied by anything gives you that thing. So 5I A inverse is simply the same thing as 5A inverse. And that's why you have this right here. So now that you have multiplied through by A inverse, you can already see that A inverse is seated right here. So this is what you are looking for. So from the previous slide, I already told you, you should make A inverse the subject of formula. And for you to do that, you can transfer minus 5A inverse here, and it becomes plus 5A inverse. So, and then you have A minus 2I. And then if you divide through by 5, it means that A inverse is 1 over 5 into A minus 2I. I mean, this looks like a cool method of getting inverse. Of course, if you compare it with things like Gauss-Jordan and you think you prefer this, you can go for it. So A inverse now is 1 over 5 into A minus 2I. So this is you expressing A inverse in terms of the matrix itself and the unit matrix. So you have 1 over 5 into A now is 3, 1, 2 minus 1, minus 2I. 2I will be 2, 0, 0, 2 because it is 2 times the unit matrix of 2 by 2 order. So A inverse is now 1 over 5, this, into 3 minus 2, 1, 1 minus 0, 1, 2 minus 0, 2, minus 1, minus 2, that's minus 3. So this is the inverse of this matrix. So the inverse of 3, 1, 2 minus 1 is actually 1 over 5 into 1, 1, 2 minus 5. Don't forget, automatically it means that this 5 is the determinant of this matrix. Can we check? 3 times minus, oh, okay, 5 is not the determinant. Okay. So because the determinant here is like 3 times minus 1, that's minus 3 minus 2, that's minus 5. So the minus has automatically entered here, that's why. Okay, so that is a simple case of a 2 by 2 matrix. Let's go ahead and look for a bit bigger trouble as we consider 3 by 3 matrix. Let's go. So look at this. We want to find the inverse of R, which is equal to 1, 2, 2. Now, this was the matrix I also dealt with under 3 by 3 in the previous video. So find the inverse of R, which is 1, 2, 2, 2, 1, 2, 2, 2, 1. So again, the first thing you want to do is find the characteristic polynomial. Find the characteristic polynomial, which is R minus lambda I. And as you already know, all the lambdas are going to get attached to the elements of the principal diagonal. So you have 1 minus lambda I, 1 minus lambda I, 1 minus lambda I, all these ones, minus lambda I. Then every other thing remains what it should be. And then since we know that the characteristic polynomial is the determinant of the difference between the matrix and lambda times the unit matrix, then it's time to find the determinant. I think we did it in that other case. So I think I'll be faster here. Of course, you're going to attach your signs plus, minus, plus. So you have plus minus 1 plus 1 minus lambda, cross this and this, you have this coming here. Then after that, you have minus 2, which is here. So cross this row and this column. This column, this row and this column, sorry. And you have 2, 2, 2 that, 2, 2, 2, 1 minus lambda. And then lastly, you have plus 2 into cross this and cross this. So you have 2, 1 minus lambda, 2, 2. So that so with that, you have all of that settled. So the next thing is just to tidy things up. So you have 1 minus lambda, then this is this times this, that is 1 minus lambda squared, minus 2 times 2, that's 2 squared. Then you have minus 2 here, there's 2 into 1 minus lambda, 2 times 2 minus 2 squared, plus 2, 2 times 2, 2 squared. We've done this before, that's why I'm not wasting time on it. 2 into 1 minus lambda, you have this. So next is to tidy things up. So this is 1 minus lambda. If you square this is 1 squared minus 2 times 1 times lambda, that's minus 2 lambda, plus lambda squared, that's this. Then minus 4 here, this minus 2. 2 times 1, 2, 2 times lambda, minus 2 lambda, then minus 4 plus 2. This is 4 minus 2 plus 2 lambda, and then that is what you have. So you can tidy up things now. So row of lambda now is 1 minus lambda into lambda squared minus 2 lambda, 1 minus 4, that's minus 3. Then minus 3, then minus 2 is here. Then 2 times minus 4, that's minus 2, minus 2 lambda plus 2. 4 minus 2 is 2 plus 2 lambda. Then we go ahead to still tidy up further. We have 1 minus lambda squared, that's lambda squared. 1 times lambda squared, that's lambda squared. 1 times minus 2 lambda, minus 2 lambda. 1 times minus 3, minus 3. Minus lambda times lambda squared, that's minus lambda cubed. Minus lambda times minus 2 lambda, that's plus 2 lambda squared. Minus lambda times 3, that's plus 3 lambda. And then you have minus 2 times minus 2, that's plus 4. Minus 2 times minus 2 lambda, that's plus 4 lambda. 2 times 2 is 4. 2 times 2 lambda, that's 4 lambda. And then, of course, like I said before, you can collect like terms. So there's only 1 lambda cube, this minus lambda cube. So we have that here. And then we have, for squared now, we have lambda squared and 2 squared. I guess that's about all. That's why we have 3 lambda squared here. And then we can also get to talk about, let's say we have lambda now. This is minus 2 lambda plus 3 lambda, that's 1 lambda, plus 4 lambda, that's 5 lambda, plus 4 lambda, that is 9 lambda. And then you have minus 3 plus 4, that's 1. 1 plus 4, that is 5 here. So this is now row of lambda, which is the characteristic polynomial for this matrix, for this 3 by 3 matrix. So, of course, you already know that if you substitute the matrix A into this, according to the Cayley-Hamilton theorem, this will evaluate to 0 because every square matrix satisfies its characteristic polynomial. That's the Cayley-Hamilton theorem. So row of A is such that 0 is equal to minus A cube. So you substitute A for lambda everywhere you see that. So that's minus A cube plus 3A squared plus 9A minus 5I. Okay. So the next thing you want to do is to multiply through by A inverse. So if you multiply through by A inverse, 0 times A inverse is 0. And then 0 minus A cubed times A inverse, that will reduce the power by 1. So you have minus A squared. 3A squared times A inverse, that's 3A. 9A times A inverse, that's 9I, because A cancels A, but you can't just have 9, so you have to multiply by the unit matrix. Then minus 5i, that's like 5 standing on its own, times A inverse, you have 5A inverse. Okay, so now we are looking for the inverse. So this is 5A inverse. So you can make A inverse. Of course, you need to make A inverse the subject of formula. That's the rule I told you in the opening slide. So you can put minus 5A inverse here. Then you have minus A squared plus 3A plus 9I. That's all that is left. So that means that A inverse itself is minus 1 over 5. If you carry minus 5 here, so that's minus 1 over 5 into minus a squared plus 3a plus 9i. So the next thing you just need to do is to bring whatever you need here. So for instance, you need, so a inverse is 1 over 5 into, you need a squared. A is 1, 2, 2, 2, 1, 2, 2, 2, 1 squared plus 3 into this a plus 9 to the unit matrix. Of course, if you square this like we've done before, you get 9, 8, 8, 8, 9, 9, 9, 8, 8, 8, 9. There's minus outside, so you bring the minus inside. Then if you multiply this 3 by all this, you have 3, 6, 6, 6, 3, 6, 6, 6, 3 plus 9, 0, 0, 0, 9, 0, 0, 0, 9 should be 0, 0, 9. This is 0, 0, 9 right here. This is 0, 0, 9. Let me do that properly. 0, 0, 9. This is 9. Okay. So then you can now do this term by term. See, you still have minus 1 over 5. Okay, there should be minus 1 over 5 outside here. Let me get rid of this. So that is equal to minus 1 over 5 minus 1 over 5. Okay. All right. So minus 9. Okay, let me change the markers for the sake of emphasis. Minus 9 plus 3, that's minus 6. The minus 6 plus 9 is minus 3. So, okay, of course, it's even easier this way. Minus 9 cancels 9 already. So you have just 3 left here. Then minus 8 plus 6 is minus 2. So minus 2 plus 0, that's minus 2. Then minus 8 plus 6, minus 2 plus 0, still minus 2. So the same here. So minus 9 plus 3 minus 6, minus 6 plus 9 is 3, Then minus 8 plus 6 minus 2 plus 0, minus 2. So the same applies. Minus 8 plus 6, that's minus 2. Minus 2 plus 0, that's minus 2. Minus 8 plus 6, exactly the same. So you have minus 2. Minus 9 plus 3, that's minus 6. Minus 6 plus 9, that's 3. So don't forget, the 1 over 5 still has its own minus. The minus 1 over 5 outside. So you have this minus here. So, of course, you can take it inside. I've always told you, as much as possible, try to avoid the problem of minus. It can be a problem, really, if you're not careful. So you have minus, just take it inside. So 3 becomes minus 3, minus 2 becomes 2, minus 2 becomes 2, minus 2 becomes 2, 3 becomes minus 3, minus 2 becomes 2, minus 2 becomes 2, minus 2 becomes 2, 3 becomes minus 3. And then you have the A inverse, which is this now. So A inverse, the inverse of the original matrix 1, 2, 2, 2, 1, 2, 2, 2, 1 is 1 over 5 into minus 3, 2, 2, 2 minus 3, 2, 2, 2, minus 3. And that's easy peasy. So you have like 4 methods for finding inverse now. So you choose the one you prefer. Is it minors and cofactors method? Is it Gauss-Jordan method? Is it by solving systems of linear equations? Or is it by Cayley-Hamilton theorem? You can choose. And then finally, you have something to try your hands on. Find the inverses of the following using the Cayley-Hamilton theorem. You have A 2 minus 1 minus 3 7, B 4 2 5 0, C 1 3 2 2 minus 7 2 5 2 1. So with this, we've come to the end of finding inverses, matrix inversion using Cayley-Hamilton theorem. This is your exercise. Don't forget, exercise. Okay. So see you in the next video. I think then we should be talking about eigenvalues and eigenvectors. Very important in matrices also. See you.